Okay, good morning. So this is the last session that I want to talk about powers and exponents, and then there are many things in chapter 1 which is now omitted from this course according to what a schoolwork is actually published. So uh, this would be the last session for this chapter. And then I give you a little bit of time to practice about some problems, and then we move to the second chapter. And then when the second chapter is finished, we will have a combined test combining chapter 1 and 2 together, okay? Powers and exponents, we just learned, we started, let me just remind you a little bit quickly. So we talked about a to the power of n. First of all, it was just a symbol that we use to summarize, to write things compactly, yes? I told you that the first list we had about the exponent n was this list of natural numbers 1, 2, 3, etc. Then we added 0 to it. Then we added the negative numbers to it, but whole in the integers, yes? So we expand our list of exponents to the set of whole integers. And then we also talked about some rules. So let me write the rules down. So we learned that if I want to multiply two powers with the same base, I can write the same base and add the exponents. We just learned that if I have two different powers with the same exponent but probably different bases, I can multiply the bases and then write the exponent on top. We also learned that for division, if I have a to the n divided by a to the m, I can write a to the power of n minus m. We also learned that if I have a to the n divided by b to the n, I can write it as a over b to the n. And we also had one rule that if I have some power, I want to exponentiate it once more. What can I do? I can write the base and multiply the exponents. So I was trying to motivate you that these formulas are not only valid for the positive part, but they are also valid for the negative part. So now today we want to officially introduce fractional powers. Okay, so let me just remind you. If I ask you what is 2 to power 3, it means multiply 2 by itself 3 times. So everyone knows how to do. Even if I ask what is 2 to the power of minus 3, you had an extra rule, so let me add it here. What was that? A to power minus n is 1 over a to the power of n. This is not a rule, this is the definition. So if I ask you what is this, then we say it is 1 over 2 to the power of 3, but then 2 to the power 3 means 2 times 2 times 2, which is 1 over 8. But today we want to talk what happens if we extend these numbers to contain fractions. So for example, what happens if I ask you what is 2 to the power of 1/3? Is there any meaning for that? Okay, so we want to understand this. I hope that you agree that either I have to give up this idea of defining it, or at least you understand that neither this definition, which was working for natural powers, nor that definition, which was working for negative integers, is not working in this case. Because I cannot say that I multiply 2 by itself a third number of times, which is not meaningful, and this is not negative, so either, but if you punch this in your calculator, you will get an answer. I will not be able to teach you because it needs more advanced mathematics, but I tell you what is the meaning of that. Mathematicians have proven that there exists a unique number, okay, a unique number, for example, x, so that when you raise it to power 3, it becomes 2. Okay? So it means that there is one unique number so that if you raise it to power 3, it becomes 2. If you ask me what that number is, exactly I don't know. I have to use different methods. But I know that based on that argument by mathematicians, there is exactly one unique number so that when you raise it to power 3, it becomes 2. This is that number x. Yes, so it is very, very uh, abstract way of defining things. So it means that, for example, if I ask you what is this one, this symbol is just asking you about that number whose third power is 8. What is that number? 2. So the answer to this is 2. So in this case, some cases, it is not hard. You can calculate it in your head. If I ask what is 8 to the power of 1/3, it is asking you about that unique number whose third power is 8. And because this number is easy, you immediately get this one. So if I ask you what is 8 to power 1/3, you immediately get 2. Yes? No, that's the same thing. I will come back to it. But if I ask you the same, I want you to understand this is the same question, but I cannot give you the exact value here. And that is not important for us. The important for us is to understand what is this symbol referring to. This symbol refers to that unique number so that if it is raised to power 3, it becomes 2. How much is that number exactly? We don't know. If you want, you can calculate approximate value of that. But this symbol, whenever you see this, it is asking you a simple mathematical question. It is asking you, what is that number whose third power is 2? Is that understandable? Sometimes you can answer that one. By the way, this is exactly as before. For example, if I ask you 10 to the power of 100, what that number is, it's the same story. If I really insist to give me this number, you have to be patient, multiply 2 by itself 100 times. It is still cumbersome, but it's more straightforward than this one. But anyway, it takes time. That's the same thing. So by seeing this symbol, you understand what is the meaning behind this symbol. In this lesson, I want you to understand the same thing for this symbol. So whenever you see this symbol, it means that number whose third power is 2. Sometimes this number is easy to calculate in your head and you get an exact answer for it. Sometimes it is not. You have to live with it. Yes? Is that clear? Okay. But there is something a little bit subtle happens if this number turns out to be even. I want to tell you this one because it needs a convention among mathematicians. For example, let me ask you this question and hopefully you can answer me. For example, I write 16. Instead of 1/3, I write 1/4. Okay? This is asking about the number whose fourth power is 16. But there are 2 of these, unfortunately, in this case. Yes? One of them, as you mentioned, is 2, and the other one is -2. Because there are 2 numbers, 2 and -2. If I raise this to power 4, it becomes what? 16. If I raise this to power 4 as a whole, of course, and then if you multiply, it turns out to be 16 again. And then there is here there was no confusions. If I ask what is the number whose third power is 2, there was only one possible scenario, and that was a number which I don't know. Okay, in this case 8 to power 1/3. I am not confused with 2 numbers. There is exactly one, and the answer is of course that number. But in this case there are 2. Which one I have to choose? There is a convention going on. You have to choose the positive one. Not have to. This is the convention that people choose the positive one for this symbol. So if I ask you this, don't write -2, even though technically -2 is also working. But by that convention, you have to write 2. So some people, if you write this, this is wrong. If you write this, plus or minus 2, that is also wrong. So there is a convention going on. So for the case that the denominator is an even number, this is the only thing that you have to be careful about. Okay? If I have even number in the denominator, always I get 2 answers. But by convention, which one is referred by this symbol? The positive one. There is also another subtlety here. Here, if I ask you, what is -8 to power 1/3? What is your answer? Again, this symbol is asking you, give me the number whose third power is -2. What is that number? There exists one such a number. Minus 2, because take minus 2, multiply it by itself 3 times. You will end up with minus 8. No problems here. So you see, when I have this odd denominator, I really don't have any trouble. There is exactly one number for any choice of number here. Positive or negative, it doesn't matter. Of course, if I choose positive one, the answer is also positive. If I choose the negative one, the answer turns out to be negative. There is nothing that I have to be worried about. But in this case, if this is positive and I choose even, always there are two answers opposite to each other. In this case, 2 and minus 2. But there is a convention going on. You are not allowed to write this. You are not allowed to write this. You have to write this. Why? Because that's a convention. Yes? This is so the calculator, if you put this number in your calculator always and always gives you number 2. Even not once minus 2. Even though minus 2 to power 4 is also 16. Another subtlety here is that I can ask you the same question, and then I want to wait to hear from you. What will be your answer here? So you see that I am just comparing these things together. 8 to power 1 over third, it was easy to answer 2. Minus 1 to the third, you will gave me minus 2. But in this case, you could say 2 on minus 2. By convention, you told me 2. But here, what happens? There are no such a number. That's another thing that you have to be careful. If I ask you, can you give me a number whose fourth power is negative 16? It is not possible. It is clear that if you choose a positive number and multiply it by itself 4 times, you end up with a positive number. If you choose a negative number and multiply it by itself 4 times, again you will end up with a positive number. So this is undefined or does not exist. So these are the only problems that you have to have in mind when you are working with fraction powers. Yes? Any questions? And there are other symbols for this one. So in principle, if I want to summarize everything, so if I have a to power 1 over n. So we need to separate two scenarios. Either n is odd or n is even. Okay? So what happens for n odd? If n is odd, there exists exactly one number whose nth power is a. Yes? If n is odd. There exists exactly one number whose nth power is a. A to power 1 over n refers to that unique number. So let me emphasize a little bit more. Of course, if a is positive, a to the power of 1 over n is also positive. If a is 0, by the way, can you tell me what happens? It is asked, if a is 0, 0 to power 1 over 3, for example. It is asking you, give me the number whose third power is 0. What that number is? Is still 0. So if a is 0, a to power this one is 0. In principle, 0 to power this one is always 0. And if a is negative, then a to the power of 1 over is still negative. So this is only for, be careful. What I have written here is only for this case that n is odd. Now, let me summarize what happens when n is even. Let me write this if you want in the future, read it. So n even. Okay. If a is positive, then there exists a unique positive, so let me emphasize here, there exists a unique positive number whose nth power is a. A to the power of 1 over n refers to that number. Of course, in this case, you will also find a negative number, but this is why I emphasized. This symbol means the positive one. If a is negative, then a to the power of minus 1 over n is not defined. But be careful. I am writing this under this when n is even. And of course, if a is equal to, again, 0 to power 1 over n, in this case, also 0, yes? If I ask you what is 0 to the power of 1 over 4, I am asking you, giving me a number whose fourth power is 0. 0. That's not a big deal here. Okay, now let us try to understand this a little bit better. So if I give you a to the power of 1/3, so now you know what the meaning of this symbol is. Okay, let me give numbers for you. Might be that's easier for you. So 2 to the power of 1/3. If you tell me what this is, I can explain it to you. But if you tell me what is the exact value, I cannot give it to you unless I use some more advanced mathematics or calculator. So what does it mean? It means that this is the number whose third power is 2. Okay? Now, if you ask me what is this value exactly, I don't know. But if I raise this to power 3, I can answer this exactly. It is 2. Because that, by the way, this is just a circular argument somehow, yes? 2 to the power of 1/3 means that number whose third power is 2. Now I am raising that number. What that number is, I don't know exactly, but whatever it is, I am raising it to power 3. So according to the definition, the answer should be 2. And this is very interesting to see. This is consistent. So they have defined it in a consistent way. You see, if you don't want to make trouble for yourself, you can use this rule, even for fraction powers, yes? So you say that I multiply 3 by 1 over 3 according to this rule, and then it becomes 2 to power 1, and 2 to power 1 is 2. So this means that the good news is you really don't need to remember new formulas for fraction powers. Whatever formula you had for those type of exponents are still valid for this type of exponents. Okay, I haven't proven anything for you here, but I want you to understand the grand picture behind it. Okay, can you tell me what happens here? It's still 2. Why? Because this, let us consider this to be the box. The box to the power of 1 over 3 means the number whose third power is in the box. So when I ask you the this number to power 1/3, I am asking you about the number whose third power is in the box. But which number is that whose third power is in the box? 2. So the answer is again 2. So it doesn't matter if you have this one and that one. And then I am telling you, you really don't need to be worried at all, because I told you the good news. The good news is that all rules will also apply in this case. So if I give you this in the exam, you really don't think about this convoluted way of defining things. You just multiply 3 by 1/3. It doesn't matter if I write it in that way or that way. The answer becomes 2 to power 1, and everyone knows that 2 to power 1 is equal to 1. Is that clear? For example, what do you think about this one? 16 to the power of, let me now bring negative and this number in. So the negative part should be used, I should use this rule for the negative part, and for this new part, I should use this new lesson. So what I do, yes? Yes, so I would write 1 over, as usual, 16 to the power of positive 1 over 4. But this 16 to power 1 over 4 is asking you about the positive number. Do you remember? This is why I explained here. For the even case, this is important. Which positive number is there whose fourth power is 16? It's 2. There are two numbers, but I'm always caring about the positive one by that convention. So then this answer becomes 2. So the numerator is as usual 1. This answer becomes 2. So I get 1 over 2. So this number is a number that is just the same number as 1/2. Or you can do it a little bit differently. If you don't like this method, this is good. It doesn't matter. Whenever you do these things in a reasonable way, you will get the same answer. For example, here, I could write what? Instead of 16, I think you are good in this. It's not a big number. You can write 2 to power 1/4. To power 4th. And then you can minus 1 over 4. And then you can multiply these two numbers. So what's the answer? 4 times minus a quarter becomes negative 1. And then 2 to power negative 1 is 1 over 2. So it doesn't matter in which way you do it. Okay? But of course, this is preferable. If the numbers are big, probably this is a little bit based on guesswork. Okay, there is another symbol that I want you to learn, and that is in this way. So sometimes people use this notation. Sometimes people use this notation. They are the same thing. Okay? So if you write it in this way, so they are equivalent. These are different symbols that are used for the same concept. So if I ask you what is the meaning of this, it means the number whose nth power is a. If I ask you what is this, the same thing. It's the number whose nth power is this a. Okay. And then there is also a convention, because most of the time we are working with 1 over 2. By convention, if this is 2, people don't write it. People don't write it. So they say just write this. So if you see this symbol without any number there, this means this is the second root. And then in this way, you read it the nth root of a. If you read it in that way. So here you read it as the second root of a, the second root of a, or you just normally you don't see like this. You see like this. So this is something I want you to write it down. You have it in the formula sheet, but I think it's very important to remember that. There should be a natural question at this stage for you. What is the question? Because do you remember the goal of the lesson was to expand this set of exponents? So today we talked about what happens if I have 1 over 3, but these are not the only possible fractions, yes? Here you see I am always talking about a fraction whose numerator is 1. But what happens if the numerator is not 1? Yes. For example, what do you think what do you think will be this number? So I want to make sense of this symbol as well, because even if you punch this in the calculator, you definitely will get an answer. How the calculator knows to calculate, I want you to understand this one as well. You know that and 2 over 3 can be written as 2 times 1 over 3. So that is up to you. You can do it in 2 different ways. You can write it as 8 to power 2 to power 1/3. Or if you want, you can write it as 8 to power 1/3 and then to power 2. Both of them. If I ask you what is this, because I just told you that this rule also applies in this new case, then these two numbers will be multiplied and you get 2/3 back. If you write it in this way as well, the same story happens. You multiply these two and you get this back. So that is up to you. You can interpret this either in that way or in that way. But I think, let us see. If you interpret it in that way, then you would say 8 to power 2 means 8 times 8, which is 64, and 64 to power 1/3. Again, it is asking you about a number so that when you raise it to power 3, it becomes 64. What that number is? 4. 4 times 4 times 4 is 64. So the answer turns out to be 4. But let us do it in that way. This is asking about 8 to the power of 1/3 first. It is asking about the number whose third power is 8. It's easier. What is that? 2. So this is nothing except 2. But then I have another extra exponent here. But everyone knows 2 to power 2 is 4. And you see that this is consistent no matter how you do it. But of course, for our brain, probably this one was easier because I have to deal with the smaller numbers. Yes, please? No, these are the only ways. Yes, but I didn't talk about that one because I think yes, that is up to you. I hope that at this stage, yes, you don't have that problem to calculate 8 to power 1/3. But yes, you are right. If it's still you want to understand why this is true, instead of 8, you write 2 to power 3 and then to power 1/3, and then you have another power of 2. Yes? If you write, that's completely okay, but I was thinking the number is so simple that I could guess here. If you cannot, of course, what you said is completely correct. You have to do it in that way. Any questions? Okay, so something that is important to realize. So let us keep the formulas here. So these formulas usually are also expressed in the form of the nth root. Yes, by the way, this is in English, this symbol on its own is called a surd. Yes? So sometimes I say write it as an exponent or write it with a surd sign, but you need to understand this is the rule. Okay, so can you tell me if I want to write this, I don't know, for example, if I give you 2 to the power of 3/4, if I ask you to write this as a surd, so you cannot immediately do it because what we have is this kind of relation, and then it is important to have this number 1 on top. So it is not like that yet. So you can interpret it in that way, again, 2 ways. You can write it as 2 to the power of 1/4 and then to power 3, but then I can use the surd sign here. What can I write? I can write the 4th root of 2 and then to power 3. So that's one way. Yes? Another way is to interpret it in a slightly different way. So you can write 2 to the power of 3 to the power of 1/4. But then I can write it as the 4th root of 2 to the 3. Yes? Or if you want, in this case, you can write the 4th root of which number? 8. But something is very clear here, because this is equal to this, and this one is also equal to this. They have to be equal themselves. So this means you found a nice rule. So if I have a nth root of a, and I want to raise it to power m, it doesn't matter if I evaluate the nth root first and then the exponent, or if I do the exponent first and then the nth root. Yes, because you see what happens here. Here I am calculating the 4th root first and then I am raising to power 3. But here I have to be patient to do this one first to take the 4th root of the answer. So here I am raising to power 3 first and then I am taking the 4th root. But the good news is that they are equivalent. Yes? So this means that this is the case. Of course, there are some exceptions you have to be careful about. So can you tell me about this first of all? What do you think about the 4th root of -5? If I write this symbol for you, what do you say? Doesn't exist, because it is asking you about a number whose fourth power is negative, but you know that even if you choose the negative number, its fourth power will be positive. So this is undefined. Okay, now let me tell you which one of these symbols is defined and which one is not defined. Be careful about these small differences. So if I write this for you and if I write this for you, what is your opinion about these? So what I'm trying to say, by this example, we are motivated to conclude this. It doesn't matter, write this one and then raise it to power m, or first raise it to power n, then take the nth root. But I'm trying to say that, of course, every formula in mathematics has a limit domain of applicability, so you have to respect that. So let me ask you a question. Which one? Do you think this symbol is meaningful? Or this symbol is meaningful? Or both of them? Or none of them? Top one is meaningful. Because even though I put a -5 here, but I have put the pair of brackets around that and raise it to power 2. What does it mean? It means multiply 5 by itself 2 times, which turns out to be 25 and positive. So under an even root, I have a positive number, I don't have any problems. It makes sense. Even if you ask me what the number is, I don't know, but it makes sense. But this one, it doesn't make sense, because you have to do this one first and then raise it to power 2. Yes, but I cannot do the first operation, let alone the second one. So this is meaningless. This is meaningful. If I want you to write something in front of it, you can write the fourth root of 25. Or if you want, you can write the fourth root of positive 5 to power 2. It doesn't matter. So you see that this formula, if you want to use it, you shouldn't use it blindly, because sometimes it is not working about these exceptions. So if n is even, a should be positive. Otherwise, this is meaningless. Okay? So whenever I write this formula, I mean that you yourself know that you have to respect the things that I mentioned here. For example, if n is even, you are not allowed to put a negative number here. So this equality makes sense if the this equality is true if the left-hand side and the right-hand side are indeed numbers. If they are not numbers, so I don't even compare them, yes? So something like this is so you know about this. Okay, so sometimes, so this is one thing, these are not in the formula sheet, but I think for you it is better at least to familiarize your eyes with these kinds of formulas. Okay, another type of formula that I want you to remember somehow, or at least be familiar with it. So, for example, we learned that if a to power some n multiplied by a to power m, it becomes, b to power n, it becomes a times b to power n. This is one of the rules that we learned. I just told you that without, of course, proving, try to motivate you, but that is not a rigorous proof. I told you that this formula remains valid if you take fraction powers. So in that case, you can also write a to power 1 over n multiplied by b to power 1 over n. This becomes a times b to power 1 over n. So far, so good. So there is nothing to remember. But in the form of third sign, it is important to realize this one can be written as a third as the nth root of a. And then this can also be written as a third as the nth root of b. This one can also be written as a third as the nth root of what number? A times b. So apparently we got a rule. So if I want to multiply two nth roots, I can take the nth root and then multiply the ones below that. Yeah, so that is something that I want you to know. Of course, again, there are some exceptions. If n is even, I am not allowed to choose negative values for a or b. So this means that this equality holds if they make sense. Okay? So that is important. I haven't written it down, but I have talked about this. So this is one of the formulas that I want you to learn. Okay, let me ask you another question. This is sometimes good. The fourth root of 25 and the second root of 5. How do you think they are related? So if you ask me, Babak, do you know the exact value of this number? I would say no. If you ask me, do you know the exact value of this number? No. But if you ask me, can you tell me what they are? Yes. I can say this is the positive number whose second power is 5. I would say this is the positive number whose fourth power is 25. Okay, this I can describe. But now my question for you is that, do you think there is any relation between these two numbers? Let us check. Sometimes this symbol is better for us. What I do, I would say that the fourth root of 25 can be written as the exponent. How? As an exponent. I can write it as 25. Can you tell me which power? 1/4. Yes? And then what can I write for 25? I can write 5 to the power of 2 and then to the power of 1/4. But I know the rule. I can multiply them. And then it becomes what? 5 to the power of 1/2. And now, can I write this as a third again? What is that? The second root, which I don't write by convention, 5. So whatever this number is and that number, they are exactly the same numbers. So this is extremely important to understand that they are equal even though they have written differently. So here, this is the fourth root of a number. Here, this is the second root of a number. But I realize the second root and the fourth root in this case are the same. The fourth root of 25 is exactly, be careful, exactly the same as the second root. Even though I don't know the exact value of this, I don't know the exact value of this, and no computer will be able to give you the exact value because these numbers turn out to be irrational, so it means that the decimal points will continue forever. Yes? But by definition, what we learn, it is completely logical to understand that there is one positive number whose fourth power is 25. There is one positive number whose second power is 5. These two numbers happen to be the same. Exactly the same, by the way, not approximately. And that is important in mathematics. We want to learn equalities between exact values. So which one is better for our brain to work with? Just definitely this is easier, yes, for us. So that is something that you also need to learn. Okay, so that is about exponent powers. This part is in the old Origo book is missing. So in the new edition, they have it. Okay, I will take that part and upload it so that if you want to work, you can work on it. Okay, but the rest of the chapter 1, which is in this book, is not relevant anymore. Okay, one thing that I want to talk about and finalize the lesson, I think you already remember about this, that is scientific notation. So that scientific notation is actually very important in practice, especially physics and chemistry, that you are facing with very, very big numbers or very, very small numbers. Okay, so what do I mean by the scientific notation? So for example, the distance from the Earth to the Sun is 150 million kilometers, yes? It's not a very big number to write, but if you want to write this number over and over again in your calculation, it's not very efficient, yes? So why is that? So people start using scientific notation. And the scientific notation, you have to respect the format. The format is this: A times 10 to some power n. Yes? What is this A? A is a real number between 1 and up to 10, or I mean up to 10. Yes? And this n is an integer, meaning positive or negative. So scientific notation has nothing to do with fraction powers. So this, if a number is written in this form, then you say that number is expressed in scientific notation. Okay, so for example, this number, is it in scientific notation yet? No. Because in scientific notation, you need a power of 10 appears number. So what you do, you can write it like this. For example, I want to understand what is going on. Of course, you can write it as 15 times 10, 10 million, yes? With 7 digits, okay? With 7 zeros. But can you tell me what can I write for this as a power of 10? 10 to the power of 7. Okay, be careful about what I'm saying here. If you say this number is equal to this number, I agree with you. But if I tell you this is, if I ask you, is it in scientific notation, you should say no. So be careful. Scientific notation means you have to respect this number shouldn't go beyond 10. Okay, so be careful. Is this number equal to this number? The answer is yes. But is this an appropriate scientific notation for this number? No, because I haven't respected that 15, this number sitting here, should be from 1, including 1, up to 10, excluding 10. Okay, so this is not correct. Okay, then what can I do then? So I would do this. I will take this away, and I write 1 over 1.5, yes, but I multiply it by 1 more 0. Agree? And then what happens here? This becomes 1 comma 5 multiplied by 10 to which power? 8 this time. So this is not only equal to this number, but it is also written in appropriate scientific notation. Yes? Okay, so for example, let me go to numbers very small. Of course, I wanted to give you the mass of an electron, but this is very, very small. So let me just keep it like this. So if I give you this number, 0. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, and then I would write 9, 3, 1. So assume that in some science, you're doing science and a number comes like this. And you have to take this number and repeat it over and over again. Writing this, I hope that you agree, this is actually not very efficient. But you want to write it as a scientific notation. But the point is different. Here this number is already above 1. Here the number is already below 1. So I hope that you agree with me. This was not hard. For this one, what I am supposed to do? Yes, but do you know why negative power appears here? Let me ask you a question. If I ask you what is 10 to the power of minus 1, what is the meaning of this? According to what we learned is 1 over 10. But 1 over 10 in decimals can be written as 0.1. Be careful. If I have minus 1, including this 0 if you want, 1 0 appears. So let me calculate 10 to power minus 2. Then it becomes 1 over 10 to the power of 2 based on what we learned. And then this means 1 over 100. But if you write 1 over 100 in decimals, how many zeros you get, including this 0?
3.
Yes? No, including this 0 too. So that's good. I mean, this is the reason that I want to include. Of course, this 0 doesn't make sense anymore because this is behind. But to make myself clear, not to make mistakes, in this case, I learn that I count that 0 in my head as well. So I have minus 2, I have 2 zeros. So then, can you tell me, if I continue this list, and if I have 10 to power minus n, what happens? This becomes 0, decimal point, zeros, a bunch of zeros, and then 1 at the end. If you consider this 0 as well, how many zeros you get? N zeros. So this is the rule that we just learned. So if I have this number, so then it becomes clear. If I want to write that number, what can I write that number? I can take that number 1. So what can I write? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes? Uh, so what can I write if I want to write it separately? Of course, if you just do it quickly, you can immediately do that. But can you tell me how can I write it down? I can write it as my 9.31, yes, but decimal point is here. How many of them, how many positions I have moved the decimal point in? 10 zeros and 1 11. So I can write this one and then multiply it by what? 10, yes, 0 0.0001. How many zeros from here? Yes. And then 11 zeros, what can I write here? 9.31 is the same number. But if I want to have 11 zeros, don't get confused. So yes, that I should have 10 to the power of minus 11. Yes. So how many? So you can think in that way. Here, where is the decimal point? The decimal point, you don't see it, so it means it is the very last one. So you move the decimal point to the left until you have a number between 1 and 10. So how many positions I have moved? 1, 2, 3, 4, 5, 6, 7, 8. Yes? So I write 10 to power 8. Here, how many positions I move to the right? 11. When you move, this is a little bit strange. If you move to the right, the power should be negative. If you move to the left, the power should be positive. So that's also one way. I'm not teaching you this. I think this is very simple. You can find your own way. But then I hope that you agree this is scientific notation. Why? Because I have an integer power of 10. And the extremely important point is that the number should be a number including 1 up to excluding 10, which is correct. So this is the scientific notation of this number. And then I think in GeoGebra you should be able to, I'm sure that if you are using a calculator, if it's scientific, you should be able to put numbers in scientific notation. So that's also helpful if you learn how to do it in your own calculator. Any questions? Yes? Yes, the lesson is finished. I will give you some time to have a break, but you have to come back and then start working. So I will give you one session to practice. Let us see how it goes, and then I will start the next chapter, okay? Yes? If you don't mind, let me stop recording, and then I will answer your question.